Welcome everybody. Today we're going to learn about logarithms, logarithm functions, and we're just going to introduce what a log is today and talk about some properties. To start, I want you to complete this warm-up. It's just solving 4 problems. I want you to do this and then think about, what your process is to solve each one of these problems and why that last one is so hard. So pause the video, try these problems. So for the first 3, we were able to find that x equals 5, x equals 6.5, and x equals plus or minus the square root of 7. And I think how I found each of these is I undid the operation occurring to x with that inverse operation. For example, x plus 5, I subtracted 5 from both sides of the equation. 2x equals 13, I divided by 2, and then x squared equals 7, I square rooted both sides, which don't forget to account for both the positive and the negative version of square root of 7. But in all of these cases, what I used was the inverse of the operation occurring to x. So in this last problem, unfortunately, we have yet to learn any operation that undoes x being in the exponent. So that is the goal of today, is we are going to learn an operation that's going to allow us to solve for x when it's in the exponent. Now, we have actually tackled problems like these. When solving exponential equations, we taught a strategy which was same base solving. So in the first example there, one way you could solve this is changing that 64 to a 4 to the 3rd power, and then saying, oh, okay, because my bases are the same, that means I can equate my exponents. So this would be x equals 3 times 3x minus 1. And then we could solve for x from there. But that kind of strategy kind of falls apart once the bases have no means of becoming the same number, like 26 and 7 in this problem below that I'm highlighting here. So 26 and 7, there's nothing I can do to 26 to make it a base of 7. There's nothing I can do to base of 7 to make it a base of 26. So we're kind of stuck. So what we need is an inverse operation of having a variable in this exponent, which brings us to logarithms. So what a logarithm is an if-then statement. It means that, if we have b to the y is equal to a, then log base b of a is equal to y. So it's a different way of writing an exponential equation such that allows us to solve for the exponent. Okay, what I want you to notice right now is that my b becomes the base of a logarithm. It's kind of like a little subscript next to that word log. And the a becomes what we call the argument. Okay, so let's go ahead and label those. And what I want you to notice is that this base b and this argument a, when put into a logarithm, it equates or equals that variable y, which is what we're looking for. So a couple of things about logarithms. First of all, saying these out loud, we say y is equal to log base b of a. So we have y is equal to log base b of a. And once again, these logarithms can be written in exponential form. So you can just make the base of the logarithm, the b, the base of an exponential equation with whatever that logarithm's equal to in the exponent. So this log base b of a equation can be written as a equals b to the y power. Let's get some practice with rewriting logarithms in exponential form. So with this first one, we've got y equals log base 2 of x. If I were to rewrite this in exponential form, I want to keep my base of 2. I want to raise that to the power of y and set it equal to x. Once again, that base of 2 in my logarithm becomes the base of 2 in my exponential equation. That argument x becomes what the exponential function's equal to, and that variable y, whatever the logarithm's equal to, becomes the exponent. Okay, why don't you go ahead and try out the next 2 on your own and see if you get them right. Hopefully you got a chance to check out the answers to the next 2 problems. And once again, these logarithms and these exponential equations, they're inverses of one another. They're inverse operations. So they kind of undo each other. So we can also go the other way. And we can rewrite exponential functions as logarithmics. So in this one, what I'm going to do is I'm going to keep my logarithm base 10. I'm going to make the argument y, and then the exponent becomes whatever the logarithm's equal to. So the x becomes what the logarithm is equal to, the y is my argument, and then 10 is my base. There's also one notational thing you can do with log base 10. Log base 10 is kind of like assumed. So if there is no base there, what that means is the base is 10. It's kind of like if you have just an x, there's always assumed a number, a constant in front of that, a coefficient, 1. Okay, let's do the next one. So this one we have 14 is equal to e to the x, e being Euler's number, not a variable, so about 2.71. So if I wanted to put this into log form, I'll do log base e of 14 is equal to x. And then same thing, similar thing, there is like a little bit of a notational thing you can do with log base e. We call this the natural logarithm, which we write as ln. So this is like, I know, a special case or special notation for log base e. You don't have to use it, but it will be used pretty frequently when talking about log base e, is ln of 14. Lastly here we've got just a bunch of variables, so we can change this to log form by taking log base a of b is equal to c. So finally, we have arrived at our conclusion of the lesson, which is bringing back the 1. So if I wanted to solve for x, for 2 raised to the x power is equal to 7, one way I can do that is I can turn it into log mode. I can say that this is log base 2 of 7, which is equal to x. What we've just found is a number. Log base 2 of 7 is a number. I could plug it into my calculator, I could get a decimal approximation, but ultimately what we found is what x is, which is the whole goal to begin with. So we have satisfied our learning objective of finding an inverse operation when x is in the exponent to find out what x is. Hopefully enjoyed our first lesson on logarithms. The homework and its key should be published for you.